So hello again. Tonight we're going to talk in the realm of radio astronomy. Radio astronomy, how low can you go? Normally when I'm talking about low and I'm talking about equipment for amateur astronomers, it's I'm looking for something dirt cheap, something that the price is so low that the average person who's a hobbyist might consider doing it. You don't have to be well-heeled or have deep pockets to go do it. But in this particular case, we'll kind of do some dirt cheap. But how low can you go is really referring to how low a frequency, how long a wavelength of radio is it possible to observe in. And we're actually going to be looking at cycles per second or frequencies less than 1 Hertz. Typically, you talk about cycles per second. This would be seconds per cycle. Very, very low frequency, very, very long wavelength. So why go so low? Or, why so low? It's for propagation of radio frequencies. There are actual uses for very low radio frequencies. The 3 to 30 Hertz range has been historically used for very low data rate, very reliable data communication, one way with nuclear submarines as a means of telling the people operating the sub that we've all just been wiped out by a nuclear war and here's your communication that tells you where to launch or whatever. So one-way communication. The reason why they use such a low frequency is such a low frequency has such a long wavelength that it propagates through just about anything. It goes through the depths of oceans, no problem. Whereas even VHF and certainly UHF would not propagate through deep ocean because of the salt content and the water. But it turns out that very low frequencies do not, people will say it propagates through the core of the Earth. It actually doesn't. It bounces off the metallic content of the core and it actually wraps around the core of the Earth. So you can have a wave that will bounce off the core, wrap around, so you can, from the center of the United States, send a signal to a submarine out in the Pacific. But in this instance, we'll be going from 0 to 1 Hertz, looking for deep space propagation, basically emissions by gas or dust that pass through gas, dust, nebulas around planets, moons, and conceivably by a gravitational field bent around stars through gravitational lensing. So very low frequencies can be propagated over very, very long distances. But actually what generates these signals we'll get to later in this presentation. So you'll hear something called the InterStellar Medium or the ISM. And you'll learn that there's a guy that a long time ago said, his name is Langmuir, that the plasma frequency of the interstellar medium will not propagate radio signals below 100 kilohertz, which is a wavelength of almost 3,000 meters. So a wavelength longer than 3,000 meters will not propagate through space. It needs something. His belief was that the interstellar medium does not have a sufficient density of metallic elements. In this case, we're once again talking about hydrogen and helium as being metallic. The metallic element density is too low to reliably convey electromagnetic radiation, radio waves, without introducing breakups. It'll start transferring the radio waves, and then it'll hit a gap of very low density space and won't be able to propagate. It's kind of like trying to shout in a vacuum. But as it turns out, maybe when he first postulated that, we didn't know what actually is in open space, but we've confirmed that since he postulated that the gas density between galactic arms has been identified about 1 × 10⁻⁴ molecules per cubic centimeter. A cubic centimeter, if you talk about the actual, how much would that be in cubic meters? That's about a million cubic centimeters per cubic meter, and 1,000 molecules per cubic meter would say, it's got about 299,792,458,000 molecules per cubic meter.
Plus or minus.
Plus or minus, yeah. I could be off by one or two. But I think that's more than sufficient to propagate radio frequencies even down as low as 1 Hertz, because all you really need are, over that vast distance, if the wavelength is longer than a meter, then all you need is one molecule somewhere in the meter and one molecule somewhere in the next meter over, and that very long wavelength will propagate very nicely through it. It won't be a very strong signal. Your signal to noise ratio is likely to be low, but the signal should be propagatable, as opposed to absolutely no, it won't be able to propagate at all. Originally, that was a good concept, but as we find, there's a lot more out there than nothing, that not quite so much nothing, and therefore it'll propagate. So I'll give you two postulations here. If a high energy source was actually unable to unload its generated energy via radio waves or via the electromagnetic spectrum into the interstellar medium, how would it do it? It can't hang on to it because it wants to, it basically wants to go back to a steady state. So it's generated a huge amount of energy. It's got to unload it. It's got to get rid of it. And what we found out with nanograv is, hey, there's a cosmic background gravity wave, very low frequency, very high, very low amplitude gravity waves. And this has been detected by the advanced LIGO. It could unload the energy in gravity waves, or if the interstellar medium actually does convey things at very low frequency, then maybe less than 1 Hertz emissions through metallic helium or hydrogen may be sufficient to propagate that. But if you don't listen to it, you'll never know. There's not a lot of study done in radio at very, very low frequencies because there's impracticalities to it, and we'll get to those. But first thing you've got to do is filter out all the higher frequency stuff. Well, if you've got a radio wave that is so able to penetrate things that it'll penetrate any depth of the ocean and it'll wrap around the core of the earth, how do you create a filter that will block that? Well, you don't. You receive it anyway. You amplify the signal to get your better improved signal to noise ratio, and then you go ahead and receive it, and you use your fancy software to pick out the noise from the signal. So if the interstellar medium can't propagate it, maybe gravity waves can. If you think about the frequency that they were looking at in gravity waves, the individual wavelength was multiple light years in length. And that propagated across the universe. A trivial thing like 1 Hertz. 1 Hertz is not a light year, it's a light second. So think about, how far light travels in 1 second. That's how long the wavelength for 1 Hertz would be. If there are magnetars and black holes and things that are energetically producing things that they want to get rid of, they can do that through Hawking radiation, which is basically going back on his original postulation that black holes do not lose information. Therefore, you have to have some kind of way of draining off the excess energy of a black hole. And so that's called Hawking radiation, named after Stephen Hawking. If there's a point between the two, and you've gone from, let's say, gamma down to X-ray, down to UV, to visible, to infrared, shorter high-frequency radio, you still have the energy. You still have energy you want to get rid of. How do you do that? Well, very low-frequency radio or gravity waves. Classical physics take is the Schwarzschild radius makes sense that the curvature of the gravitational field of a black hole will stop anything from getting out of it, except that Hawking radiation. So maybe. I think it's a growing science. But what we found is that, well, if you're eventually going to become a black hole, you might have an intermediate stage of, let's say, I don't know, a neutron star or a magnetar, pulsars. These things rotate very, very fast. And so you can't discount the energy of rotation in a black hole. Well, you've got to admit that. You've got to get rid of it somehow. And maybe the reason why we don't see wavelengths coming out is because of the instruments we're using to look at them. We're only recently looking in very low frequency gravity waves, and they're there. It's kind of like, was there ultraviolet and infrared before we created instruments that allowed us to detect it? Yes, we didn't create them, we discovered them. And as we found out with nanograv, hey, there's also gravity waves out there that have been out there and are almost everywhere. I won't say everywhere, I'll say almost everywhere. And it wasn't until we created the instruments to detect it that we knew it was there. Well, if we start studying radio emissions at the very lowest frequencies, very longest wavelengths, we may find that there's a lot of that out there that we just never knew existed. But you never know until you try. So some people might say, well, why don't we just call 1 Hertz direct current? You know, the wavelength is so long and it's so flat and it changes so slowly. Yeah, if we're sampling at, kilohertz or megahertz levels, for all intents and purposes, this will look like direct current because it doesn't go very high or very low. It's around a very, central location because the peak doesn't get high and the peak doesn't get low. It's just very elongated. So we might be confused in thinking that some of this stuff at the lower frequencies, it just sounds like direct current noise. It's not actually being generated by things in space, but as we found with gravity waves, when you start looking as the wavelength can be even longer, maybe it is out there. So I did this correlation between frequency and wavelength. A frequency of 1 Hertz is the speed of light in 1 second. So the wavelength of 1 Hertz is essentially the length of the speed of light. So almost 300 million meters or 186,000 miles for one wave. The diameter of the Earth is about 8,000 miles. So a frequency of 1 Hertz is many times longer than the diameter of the Earth. So how would you actually receive that? And as you see, as you get to fractions of 1 Hertz, it gets even longer and longer and longer. So here's the thought, amplitude versus wavelength. In astronomy, when we're looking at imaging, we always think of it as if the amplitude is not very high, we're going to need to increase our exposure time, our duration, so we collect more photons to make the image brighter, to give us more detail on it. And that makes sense from a visual perspective. But as you get into other wavelengths, you find that you can't really do that because the sensor chemistries have to be designed for the specific wavelengths that you're talking about. It's something called the band gap. This is the wavelength beginning and end that the particular sensor is sensitive to taking in the photons and producing electrons. If the chemistry of the sensor is not right for the particular wavelength, it might not detect it sufficiently, it might not detect it at all. So materials make sense. And how do we detect this? Well, you have to have enough photons coming in, getting converted to electrons. We then take a charge of those electrons and we read it out with an analog to digital converter that measures the amplitude as a voltage. So here's something that makes you go back and rethink some things. So if you remember back to the days of AM radio and you ever looked at the field of antennas of an AM radio station, it was just a lot of giant towers that had a wire going between them. They're called dipoles. In order to make it inexpensive to produce very low frequency transmitting and receiving antennas, as the saying goes, you just throw a wire up. That's what you did. But we continued to do that. So if you look at the very first mobile telephone, the old Motorola handset, you'll see that it had about an 8-inch long, what they call rubber ducky antenna. it should actually be many times that length, but there's a coil, that lump in the bottom of the antenna that made it from the antenna being about almost a meter long. When we came out with things like the first generation of home cordless phones, and they were at about 400 megahertz, we had a telescoping antenna on the base in order to make the antenna length match a quarter wavelength of the frequency it was running at. But you can see that the stub antenna on the mobile unit did not have to be that long and was actually a coil tuned to the specific frequency. So we started to move away from enormous lengths of wire to coil lengths of wire to where we are today, which is, anybody ever notice an antenna sticking out of a modern mobile phone? No, because they use things called fractal patch antennas. You don't actually see an antenna sticking out. It's inside the phone, and it looks about 2/3 the size of a postage stamp, and it looks like a little piece of copper foil that's sort of this weird pattern of jagged lines. It's called a fractal patch antenna. The reason why it works is we have low noise amplifiers that might amplify that signal about 1,000,000 to 1, and therefore it'll increase the amplitude. And by increasing the amplitude, we can now use a very high frequency analog to digital converter. And then we use software, digital signal processing software, to reconstruct that wave to get the signal out of it. And if you think that, well, that's because we're on high frequencies now, we don't need those things anymore. In the 4G LTE band, it supports 600 megahertz. 600 megahertz has a wavelength of 1/2 meter. I don't see any antenna sticking out of my cell phone. We've progressed from having giant chunks of wire or wire coils to, we just sample the data like crazy and then we reprocess it in software. But we still need some way of saying, I need to get rid of all the higher frequency junk, because if I receive a very wide range of frequencies that's well above my 1 hertz range, then I'm going to be picking up all kinds of noise. And we'll talk about what that noise might be. But you want to block the higher frequencies and pass only the lower frequencies. But since very low frequencies, very long wavelengths will pass through just about anything, you can't do what we do with cameras. With a camera, you throw an infrared blocking filter on the front and you block out all the infrared that would otherwise overexpose your image. Well, you can't really do that with low frequency radio. So we receive it, bring it in, recognize that it's there, and then you write software that clips it out. So what other kinds of frequencies are doing things in the same ballpark? Turns out there's a lot of stuff going on between 1 hertz and 100 hertz. Lightning and the solid metallic sphere inside the Earth's core radiate. Lightning produces primary and harmonics at 7.83 hertz. That's like the vibration of a lightning strike. And then the Earth's core, the metal in it, resonates at 14.1 hertz. How do we know these things? Well, obviously, when we were looking to use the ELF band 3 to 30 hertz for military purposes, we found these Schumann resonances and went, okay, let's not line our frequencies up on 7.83 or 14.1. How about we do something in the 3 to 30 hertz range? And then's when they found out, oh, there's some folks out there already doing things with that. Who knew this one? The folks that run pipelines. They want to communicate with what is known as pigs. If you saw the James Bond movie where they had the thing that was going down the pipeline, there's a gas pipeline that had no gas in it yet. There's this trolley that runs inside the pipe and it welds the pipe segments together, and it's got cameras on it for inspecting things. This is called a pig. If you understand a Faraday shield, it's a metal pipe. How do you get the radio signal to and from the pig? You transmit at 22 hertz. So the very long wavelength propagates to and from the pig. but it's not good for sending video or getting audio because obviously the wavelength is too long. But it's great for sending little text commands to the pig to say, start, stop, go faster, go slower, whatever. 22 hertz, pigs, not the nature kind, the man-made kind. And then think of two other frequencies that we transmit a lot at. Outside the US, 50 hertz. Inside the US, 60 hertz. This is the power grid. Well, how much power are we transmitting at 60 hertz? Megawatts, gigawatts. Oh, okay, I get it. The military decided, well, we're not going to be able to use those Schumann resonances, not going to do the 22 hertz where pigs are at, not going to do 50 or 60 hertz where the worldwide power grid is. How about 3 to 30 hertz? And that's when they found out 30 hertz is a no-go for large mammals living under the oceans who get an earache and bloody ears when you start communicating at 30 hertz. We also found out that there are things in space that have noise at less than 30 hertz. So we're finding all these natural frequencies out there that there's stuff on it. But we don't do radio astronomy at that level because nobody wants to. Now, yeah, everybody thinks I gotta have an antenna wire longer than the diameter of the Earth. Like, no, you don't. Does your cell phone have a 1 meter long antenna sticking out? No, we do things differently nowadays. So software-defined radio in the 0 to 1 hertz range. Well, what are we going to use for our detectors? So I put together this lovely little chart of what kinds of chemistry, what kinds of materials are good, have a good band pass, a good spectral bandwidth, a good spectral response, quantum efficiency for various frequencies. So if you're looking at the the very higher frequencies, you want silicon, you want mercury, cadmium, telluride, germanium, indium, gallium arsenide, and lead sulfide. Lead sulfide will get you down into the longer infrared wavelengths. But what about radio? What chemistry do I use for radio? Well, radio has had a trick up its sleeve for a long time. It's called superheterodyne. So what a radio receiver does is it has an antenna, which may be tuned to a particular frequency to attenuate or amplify certain frequencies and block out others. It can have a low noise amplifier that blocks certain frequencies. It can have, if it's not very low frequency, then it can have, particular kinds of filters, high pass, low pass, band pass, notch, cutoff, to decide what you want to pass and what you want to block. But what we've actually got on the inside of our software-defined radio is what is known as a superheterodyne circuit. What it does is it has a little oscillator that's of a known frequency, and then what it does is it produces a variable oscillation that beats against that, and that they adjust for whatever frequency you want to receive on. And the beat frequency against the intermediate frequency generates the actual radio frequency that you're receiving. So the radio doesn't actually have to have the ability to tune from like 0 hertz to 1.4 gigahertz. All it has to do is tune around a specific band pass on this intermediate frequency, and then it adjusts the beat frequency oscillator, the variable oscillator, to direct the particular radio frequency that it wants into the intermediate frequency to produce the radio out. So it can do that, so it only needs one back end to do the analog to digital conversion. But much like a stereo radio has a left channel and a right channel, in order to get both phases of a radio wave, the I phase and Q phase, you need actually two analog to digital converters coming out. One that picks the signal up this way and one that picks the signal up this way. And you bring that out as two different analog to digital conversions. Wouldn't it be really cool if we could do that with astronomical imaging? If we could actually say, I want to go to every pixel in my camera and say, now it's time to start receiving red. Tune the imager to red. I wouldn't need any filters anymore. But unfortunately, just like the higher frequencies don't work like radio, radio works a particular way, and the imaging chips work a different way. So sorry, you can't do that. Maybe someday. So here's our software-defined radio. So it's about that size. And what it's got on one end is a screw connector. It's an SMA threaded antenna connector. And on the other end, it's got a USB host plug. So it plugs into the computer. And what it does is it brings the radio signal from the antenna in over the coax. It does that little phase lock loop down to an intermediate frequency, does the split phase analog to digital conversion, and then it brings it out as a high-speed block transfer out the USB interface. And these devices are about $35. And you can actually receive anywhere from 24 megahertz to 1.7 gigahertz with one of these devices. You can tune anywhere in there. But they have a neat ability that if instead of going through the tuner, you go straight from the antenna, straight to the analog to digital converter, you can pick up either of the two phases and directly convert it. So it can actually tune all the way down to 0 hertz if I wanted to. But if I wanted to do it with a higher degree of precision, you can actually buy a box you can stick on the front between your antenna and the tuner. They will actually take a particular range of frequencies and through electronics and coils uplift that. So it'll take the lower frequencies and do an uplift of that band to the low end of the tuner's frequencies. So you can actually tune like 125 megahertz at 300 hertz. So it's just an uplift. But since we're going to be doing direct, we can go direct to 0. We won't need this uplifting capability. Not that we're going to be needing it, but what if I've got a really high frequency signal that's way above my tuner? Yeah, there are things you can buy called a down converter that you normally see these on satellite TV receivers. They put the down converter out at the dish to bring the signal in so that instead of the signal being ultra high frequency, which doesn't propagate too well over cables and through walls and such, they bring it down to a lower frequency, which makes the TV tuner electronics much simpler. But we're not going to need one of those. So here is the software-defined radio application called SDR Sharp. It's written in C#, so it only runs on Windows applications, Windows systems. It's free to download. The company's called AirSpy. You can download the software. You get one of those dongles, plug it into your Windows PC, hook up just a simple little wire-based antenna to it, and you can receive it low frequency. If you ever attempt to do it, go back and look at this video. I give you all the different steps and all the different configuration stuff you have to do to successfully receive at 7 hertz or less. I'll leave it there for a second so we capture it in video. And here's, as the saying goes, here's the pudding, here's the proof. I set the bandwidth. The bandwidth, the smallest bandwidth I can make is 10. So I've got 50 hertz right there in the center. And then I go out to the left and out to the right. And that sort of grayed area, that's my actual band. And you can see the wave. But notice how the wave's got flat spots on it. It's being confused by how slow the wave is changing. So it thinks of it as a steady state, like a DC voltage. So I narrowed it down further. This is down below 18 hertz. And you can see that it's so confused about it being DC, it actually tries to create a little square wave there. Because the wave changes so slowly and the amplitude difference is so small that it just thinks of it kind of like a rounded off square wave. So what you have to do is actually receive it for a very long period of time, take the data out of the application, and then go integrate it through some Python script out, off the SDR Sharp application. And here's how you do that. So if anybody wants to attempt it, you can use SDR Sharp to record the data as a wave file. and then you can go in and pick apart the wave file to find out what the actual data sample values are, and then you can reintegrate that back into the very long wavelength. So just as going down the rabbit hole here, I had to look up the U.S. Department of Defense's efforts at doing very low frequency radio. So from 1989 to 2004, the Department of Defense, basically the Navy, used ELF for communication with submarines. They actually deployed it, tested it, made sure it worked. The higher frequencies would not penetrate deep salt water, even rivers and lakes. Not that we have submarines in rivers and lakes to the best of my knowledge, but the description of the program actually said they tested it in oceans, rivers, and lakes. The names of the DoD projects were Sanguine, Seafarer, Austere ELF, and Project ELF. Well, they only looked in the 3 to 30 hertz bandwidth. But when they found out that it causes problems with undersea mammals, they changed the frequency to 76 hertz. So I guess the whales, instead of going deaf and having their ears bleed, they just get numb in their ears. So we changed the frequency. But internationally, other governments like China and Russia are still working in the 3 to 30 hertz band to talk to their submarines. Talk is kind of a weird way of describing it. The data rate is very low. A code group is a number of characters, and it takes 15 minutes to send a single code group. This is seconds per bit, not bits per second. No voice, no audio, no graphical images, no video, text. So if you think back to the early days of computer communications, and you had the acoustic modems that used the handset of the phone, and the early speeds were 50 bits per second, or 50 baud. This is actually 1/50th of a baud. So very, very low frequency. But we found out that there are things out there in the universe that seem to be sending in the 0 to 1 hertz range. So it's worth taking a look at it. But here's something you might think, well, if I can go down to 1 hertz, how about negative hertz? Okay, all the signal does is get inverted. So if you're actually tuning, you can tune below 0 hertz and you get negative hertz, but it folds back on itself as the inverse of the signal. So just slide it back over to positive numbers because it's the same thing, just inverted. So I thought this was a little weird that the FCC, the U.S. Federal Communications Commission, does not allocate transmission frequencies below 8.3 hertz. They basically say, you want to bother yourself, go knock yourself out. They won't allocate you a transmitter, but they will bar you from transmitting. So the Schumann resonance frequencies, they're aware of that. They don't worry about it because who's going to transmit with all that noise already there? But what about the clandestine stuff? You are not allowed to transmit in those ranges. Think about it this way. If in the 3 to 30 hertz range, my wavelength is so long, I can't have 2 transmitters because they would interfere with one another. So only 1 transmitter is allowed at very low frequency. Nature doesn't care. Nature will transmit at whatever frequency it wants to transmit at. But man-made radio signaling, if you want to transmit at these very low frequencies, you have to get an international agreement to do so because 1 transmitter is like shouting across the entire band. Nobody else can be heard. And if you're FM modulated at that lower frequency, literally nobody can get a word in edgewise. So they just deny all applications for transmitting in those frequencies. But we're receiving, so we don't really care. Now, the reason why I looked into the military using low frequency is not simply for curiosity, but also maybe they learned some things that I can, plagiarize. But it turns out, nope, because there's a lot of constraints on transmitting. Apparently, they're still using very long antennas to do their transmitting at these very low frequencies. But remember, 1 hertz is larger than the diameter of the Earth. So if they're at 30 hertz, 1/30th the diameter of the Earth. So how long an antenna do they have? Well, long enough antenna that the transmitting station is out in the middle of the United States, out in the middle of nowhere. And there's only one of them. Well, how does the submarine transmit back? The submarine is not long enough. They could not create a long enough antenna within the internal nature of the submarine to transmit back. So the submarines are receive only. Think about this for a moment. The movie Star Trek IV, where somehow the whales are communicating with the extraterrestrials. If you're way out in deep space and you're transmitting on a very low frequency, that kind of low frequency that gives whales an ear bleed, maybe it's because there's a signal coming from out there that the whales can hear. But I think that the US military is no longer using ELF because it was just too big of a problem for wildlife. But what I think they might be using, and that's where there's so much interest in G2 muon at particle physics here in the US, is if you can modulate something, you can use it as a carrier, and therefore you can communicate information on it. You can make radio data out of it. We already know that we have the ability to generate muons from fission-based reactors. And we have fission-based reactors at power plants in the US, at military plants in the US. We have particle accelerators that can generate muons. We also know that we can switch the particle accelerators off and on. So if we're generating muons and we can switch the muon generation off and on, we can modulate muons. And muons are going to pass right through the Earth. So if you want to communicate with a submarine, muon modulation might be one way to do it. But how would the submarine send back? Oh, yeah, that's right. Nuclear submarines and aircraft carriers have fission reactors on board. So they could also modulate the generation of muons. Unbeknownst to anyone, we could be already communicating using muons as our carrier. But until somebody starts researching it from the public sector, I'm sure it's on a you don't need to know basis. But if you just want to receive in the 0 to 1 hertz range, $40 gets yourself a USB dongle, a Windows machine, the analog to digital converter. Pick the Q phase because the Q phase seems to have more signal and less noise on it. And then we can record that and pick the data apart. So I started writing some Python, and there is already a Python library that's sort of off the shelf that supports the basics of wave file picking data apart. And there's already a graphical plotting library. And there is a library called NumPy. It's the numeric Python library that allows you to do scientific analysis of large chunks of data. So you can generate the wave file in SDR and then read it in a Python script and then plot it out if you want to. And you can do things like statistical analysis. You can identify min and max and mean and do all those nasty things you learned about in high school and college on large bodies of numbers and then produce variances and statistical means and such. And there's actually a library called Pandas that I found out Microsoft Excel now actually supports Pandas Python. So if you're on Office 365 and you're getting your latest updates of Microsoft Excel, where you would normally put a formula in a cell, you can actually call up Python and put a script in there. I thought that was cool. So in conclusion, if you recall not being able to listen to audio frequencies below what humans can hear at, until we actually did that, and we did that out in the wild, we didn't know that elephants are actually communicating with each other across, about 5 to 10 miles distance on a normal basis through very low frequency audible vibrations. We couldn't hear it, but they were talking to each other. And when we developed the technology to pick it up, we found, oh, look at this. There's communication going on that us silly humans can't even perceive, but it exists. We didn't invent it. They invented it genetically, And we learned that we thought elephants didn't really do a lot of talking with each other. Turns out they're pretty much chatty Cathys, just at a frequency so low we can't hear it. Well, as we look in different wavelengths of light and radio, we're finding all kinds of noise out in the universe, including all the way down into gravity waves. So maybe if doesn't cost too much, it's dirt cheap to do, start taking a look at the 0 to 1 hertz radio spectrum and see if the universe is speaking. But if we choose not to listen, it'd be like choosing not to listen and finding out that elephants communicate at low frequency. We could find that the universe is out there communicating at very low radio frequencies, and it'd be a sad state of affairs for the supposed most intelligent species on the planet to just take a deaf ear to it. Take a listen, see what you hear. Lots of links. Links and links and links. Comments? Questions?
I have a comment.
Yes.
I have 3 comments, and then it's all tied up into a question. So you have to listen to my comment before you answer. Don't answer.
I'm all ears and no mouth until you say so.
Okay. My comment is that years ago, many years ago, and I gather that things have improved in the radio wave industry because there was a lot of information that was given and saying that there were misinterpreting and that it was having I can't think, I keep trying to figure out what they called it. It was like you would get the waves, but they would have artifacts and stuff in it, and you would have collision. There would be information that you would get that wouldn't be correct. And it seems to me, from what I've looked at this, it seems like it's a lot of work and a lot of information. And when you say to pick it apart, it's not like you could go out and look at the stars and then, interpret maybe from filters or something like the colors or something. It seems like there's a lot of work, and it's very hard, and it's not, originally at least, it was very hard to be accurate with it. They weren't going to these low regions when they were talking about this. Probably the most I know about radio waves is actually from science fiction. And a lot of times they'll say, well, somebody was using a can opener and we got that interference and we thought it was a wave. It was like a comic, information. Or there's some other kind of, they think they're communicating with a space alien, and sometimes they are. And it's with the radio wave because that's supposed to be a more of a universal language, maybe, I gather is what they're saying. I find it interesting, and I'd like you to give me comments, and if they have improved things so that it's not so hard, I don't know, but it's interesting. Thank you.
I don't think amateur radio astronomy will ever be at the off-the-shelf appliance level. So it'll always be a do-it-yourselfer kind of project, much as if you think of amateur astronomical imaging, astrophotography, there's a lot of people that believe it now to be sufficiently advanced to be point and shoot, and they'll go out and spend like $10,000, $12,000 on, I got to get the right mount, the right telescope, the right camera, the right software, and then I just push a button and I get the Orion Nebula. It's still not there. You might get a okay picture, but you're not going to get something that somebody that invested 5 or 10 years and learning all the nuances can actually crank out on a regular basis. Same things in radio astronomy. There are some things in radio astronomy that even the amateurs that I interact with at Sarah, the only thing they want to do is hear excited hydrogen. And I for the life of me, they can't see the forest for the trees. If all you're looking for is excited hydrogen, and that's a band that from Earth, we're not allowed to transmit on that because it's reserved for radio astronomy. That is the last place that extraterrestrials were ever going to be transmitting, because excited hydrogen and even excited helium put out so much radio noise to the universe that they're never going to transmit on that. They want a quiet spot on the dial. And so, go ahead and listen to hydrogen masars all you want, but you're never going to find the extraterrestrials on those frequencies. You're going to find them where the listening is better. What's the old saying? I lost my contact lens. Okay, where did you lose it? Down the street. Well, why are you looking at it here? There's a street light overhead. The light's better. Same sort of thing. They want to listen to excited hydrogen because that's real easy to listen to. Well, I want to listen where it's more difficult. I want to listen in the 0 to 1 Hertz range that propagates just about anything in the universe without it getting disrupted. So that's where I want to do. But there are things you have to do because it's not an off-the-shelf appliance. So, yeah. Is it tough? No, you just have to learn some things. Is it the thing that everyone's going to be doing? Not anytime soon, because you have to know so many different disciplines. You have to understand certain aspects of physics, astronomy, electronics, software, even statistical analysis, which I need to brush up some on. You need to know all that stuff before you can get a result. And the result is just going to be a signal. I detected a signal. And then you can point the antenna and go, it's coming from there. But that's about all you can do. You're not going to get a picture of the Orion Nebula at 1 Hertz. That's just the wrong concept to try and apply to it. It's like saying, I'm going to go buy a used VW Beetle and I can take it off to war because it's tank-like. No, it's not. They're different things. So radio astronomy, although it says the word astronomy, is different than optical astronomy, which is different than infrared or ultraviolet or X-ray or gamma astronomy. They're all astronomy. They just do it differently.
Thank you.
Okay. Comments? Questions?
It's interesting to think about this because the world seems to be worried about faster and faster frequencies.
Yes.
And I guess they've lost track of what's going on at the low frequency end.
Yes. I think they have a psychological bias as I want to send a TV image with audio. Well, how much data is that per second? Well, I want to send the video at 30 frames per second and the audio at 2 channels of 44 kilohertz. That's a lot of ones and zeros. That's a lot of banging bits up and down. So I need a lot of bandwidth. Where am I going to get that big chunk of bandwidth? Higher frequencies.
Yeah.
So we're talking about megabits per second of data transfer. A 4K video with typical compression takes a little more than 6 megahertz of bandwidth just for one channel, just for one video channel. We're now going to start talking in the not too distant future about, hey, everybody's pretty much got 4K. Let's go to 8K. Well, when you go to 8K, it kind of quadruples. So how do you sell faster internet? You make something demand a faster internet, and then you can sell faster internet. Well, if everybody was sending just text, who needs a faster internet? But now that we're sending 4K video with, Dolby surround sound, and I need a lot of megahertz for that. So you can't go with your 2 megabit internet. You're going to need at least 10 megabit internet. Oh, you've got multiple members of your family in the house all wanting to watch 4K at the same time. You're going to need the 100 megabit. Oh, you want our fiber. Our fiber is going to get you gigabit. Maybe not, but we're going to sell it to you that way. So the only way you can make more money is by investing more money to have more bandwidth at higher frequencies. And there's an upper limit.
Yeah, the first example of that, it would be like AM stations are mono because, only one wave of sound, and then the FMs are stereo because they have more bandwidth and then they can transmit more.
Well, actually, there exists a standard for stereo AM. but it doesn't get rid of the noise. It just uses two channels, and then
Yeah.
it merges the two channels together to give you left and right. But
Yeah.
FM actually modulates by a frequency modulation, not amplitude modulation. So as the amplitude varies due to noise bursts and spikes, could care less. The thing about FM modulation is whoever the strongest transmitter is on that frequency owns that channel, which is why there's a gap between all the FM radio stations. If you ever look at, well, this station's at this frequency and the next station's down is at this frequency, you can almost see the spacing between the stations. That's so that one doesn't step on the other. But since FM doesn't go that far, doesn't go anywhere near as far as AM, FM frequencies can be reused. So if I'm in Southeast Florida and I'm on 93.1, in North Florida, there can be another 93.1, completely different call sign, completely different station, and they won't interfere with each other because the FM signal won't propagate that far. Except at night, if you happen to have a lull in the solar radiation from the sun, and now they can interfere with each other. And you might notice this if you're ever driving on the highway out in the middle of nowhere late at night and you're trying to pick up that really weak FM station, you'll notice you can pick up the one from South Florida, but you're also picking up the one from Orlando. And it's the same station. And as the amplitude goes up and down, you're going to hear from this station, then that station, then this station, then that station. And until you get
Yeah,
close enough,
that
where
happened.
one's loud enough, one's high enough amplitude to override the other one. So there's all sorts of shenanigans you can play in the radio bands to have your way with it. But the FCC in the US is the governing body that allocates all the frequencies. And sometimes they have auctions and they get to pit one corporation against the other. Who's going to pay the FCC more money for that precious bandwidth?
Yeah. And the other guys have to live with it. Yeah.
Well,
And the other point is that there is no one tiny little space for listen to meteorites or meteors going in the atmosphere. There is no empty space on radio here at
well,
all.
here's the weird thing, and because I'm a member of SARA, I know these things. In the US, because we no longer transmit analog, basically amplitude data on the lower frequency bands, because we reallocated those as additional bands for mobile radio, for cell phones. Remember when they had the whole, got to get all those analog TV channels to go away, and we're going to switch to digital TV channels? Well, when you did that, the frequencies changed, and all that lower bandwidth got re-auctioned off for mobile phone use. But when they did that, they made higher levels of modulation, so you no longer had these amplitude waves propagating everywhere. Guess who used the amplitude waves? They were just background sound. Meteor hunters. Because the background amplitude signal would act like a radar. And as the meteor would come into the Earth's atmosphere, it would shift the signal. It would distort the signal. And based upon having multiple transmitting frequencies of these previous analog TV stations, you could tell which direction the meteor was traveling in and where to go find it on the ground. When they converted all the radio stations from analog TV to digital mobile cell service, their free background radar went away. So now SARA in the US and down in Australia, they're starting their own program to do this. They're going to be working with the FCC in the US to allocate very narrow band analog amplitude transmitters that act as beacons. So you put in the US maybe half a dozen beacons that are always transmitting a known signal. And then when the meteor shower comes in, you can use the reflections off those signals as your radar to go find the meteors.
You're talking about radio like AM, FM, and just the last 2 weeks, I heard something in the, I haven't seen it printed. I don't even remember the news station I was listening to. It's probably when I was changing channels or something. And the radio station said that there was, I don't know what state it was. I don't know. I haven't heard anything here in Florida. So, but there was something about that they wanted to do away with the AM stations, that they were asking people to sign up on a petition because it was going to go through the government to do away with the AM and just have FM. And I didn't understand any
Okay,
of it.
I know all about that. And what's happening is, if you think back to internal combustion engines in cars, they would have a large capacitor on the spark plugs on the distributor. The reason is that very ratty high voltage caused radio interference in the particular band that was AM radio. So you always knew if you were driving past or had a problem with that capacitor in your car, because your AM radio would go to crap. So you recognize it, you take it into the shop, you get the capacitor changed, and now you can listen to your AM radio again. Well, imagine that at a much higher magnitude problem called electric vehicles. You've got the commutators in electric vehicles spinning at many thousands of RPM, making just radio hash in the AM band. So how did they solve the problem? Well, the electric vehicle manufacturers decided they're no longer going to put AM radio tuners in their cars.
Of course not.
So you'll find FM, you'll find digital FM, you'll find FM stereo, you'll find satellite receivers, all this wonderful advanced electronic radio stuff in the radios in electric vehicles. And it's not just Tesla, the other, GM and Ford and Stellantis, they're all doing this because the electric motors put out such a hash on the AM band that your AM radio is just impractical. So they're petitioning the FCC to make, much like they made the analog TV channels go away in the US, they want to make AM radio go away in the US. And people are crying about this because there's probably over $1 billion of advertising money on all the AM radio stations that would no longer have a cheap home.
That's it. Mm-hmm.
Yeah, and the other problem is that far away, like in mountains, sometimes FM doesn't work. And the only thing is AM, and a lot of people like have difficult to get TV or even internet. And then the FM radio is the only, mass communication.
The AM radio, yeah. So I see it as, it's going to be an interesting fight to see whether the general public wins that can still use AM radio, or whether big business wins because it's a nuisance to explain why your EV has poor AM reception. When the car is sitting at a traffic light, it's not emitting any AM frequencies. The moment you put your foot on the pedal, and as the vehicle accelerates, the AM noise gets higher and higher frequency. So you get a whine going to a piercing. And who wants to hear that when you're trying to listen to high school football scores on the low AM frequency, So yeah, they want to make the thing that has a problem go away because there's no practical way for it to continue doing what it did. But
That does not sound good.
That's the whole thing.
I know I have trouble with AM when I'm in my car at night.
Mm-hmm.
It will start to get a lot of static in it. And I don't have an electrical car, but, I have gadgets.
Yes, but there's so many electric motors around you in society nowadays, and so many electronic computers and everything. They all produce hash interference, radio frequency interference in the AM band. And there's no practical way to shield your receiver from that. The transmitter just has to up the signal amplitude. But the problem is they don't want to step on each other, because even AM radio only goes so far before the signal frequencies get reused. So you may have a Southeast Florida radio station using 560 kilohertz, but you might also have a Portland, Oregon radio station using 560 kilohertz. And at night, the AM transmitters actually have to dial down the power because solar propagation goes away and the very long AM signal can actually propagate halfway across the US.
That's true. Mhm.
So, yeah, it makes it more difficult to successfully and reliably receive your local AM radio station at night because they have to turn down the power on the transmitter to avoid stepping on a station that's way outside your receiving range.
Mm.
The physics of radio.
Yeah, the politics too. That they're actually putting this on a ballot somewhere.
It's not going to be on a ballot. What it's going to be is the FCC does this occasionally. They put out requests for public comment. And what the FCC will do is say, we don't know any better. We'd like to make AM go away for the following reasons. Anybody got a problem with that? And if the only people that complain are a few thousand of the general population that are in the know versus millions of dollars from corporations going, please make it go away. It's a pain in their butt. Guess who's going to win?
Yeah. And this business of auctioning off frequencies, it plays hob with that.
Oh, yeah. Well, remember, T-Mobile did not buy a small fry carrier known as PCS because they wanted the business. They bought them for the wavelength because it was cheaper to buy up Metro PCS as a company to own the wavelength than it was to try and allow it to go under and go into auction and then maybe have to spend billions of dollars to get the frequency.
Right.
It was cheaper for them to buy Metro PCS and suck it into T-Mobile and then change the frequency.
So all the people that are on AM
Yes.
can't switch over to FM. Is it just common?
No, they can.
FM?
They can, so long as the station is local. If I'm in South Florida where there aren't any mountains except garbage piles, there's really not much purpose in AM because I can receive AM, or I can receive FM, or I can receive FM stereo, or I can receive FM digital stereo. And it's a much more pleasant experience to receive FM digital stereo than AM. It's just by tuning the dial. Just push buttons on the radio.
Yeah, but there's some college stations that transmit in AM that I like to listen to.
Yeah, that's what I'm thinking too.
Nope. The FCC has a way out of that. The FCC allows for universities to file for, you remember me talking about that gap between FM radio stations?
Yes.
Well, that gap is too wide. That gap is back when FM was an analog transmission mechanism. You needed all that safe zone. Well, as we've gotten to better FM transmitters and receivers and gone digital, that gap between them, there's room enough for another small power transmitter that does digital transmission to be in there. So if a university with a cheap radio station can afford a digital FM transmitter, they can allocate that with the FCC and have their university radio station, and it sounds much better.
Well, then what about the ones that are not with the university or just stations?
If they're not in a mountainous area, then yeah, that's a business that's going away. If they're in a mountainous area, then they have a reason to continue to exist because AM will go over the mountains where FM will be blocked by the mountains.
But I'm thinking if AM goes away, then anything that's played here in Florida will go away that's on AM.
They'll just move to FM.
They can just, but it's more expensive, you're saying? That's why they're not on FM now?
They have a lot of wool out there that are covering people's eyes. The companies that own the big commercial AM radio stations, they also own the big chains of FM radio stations. So if you say, I want to
It's
change
probably
the,
all owned by CBS or, the other one, something
so
fast.
if you listen to your favorite FM radio station and it's a part of the iHeart Radio network, go listen to your AM radio station. And if they say, we're a member of the iHeart Radio network, they're only transmitting on AM because it offers a cheaper tier for advertisers.
Mm.
The content is just, they're going to replay sporting events. It's going to be talk radio. It's just filling the airwaves. They could put that same content on FM.
Ooh.
It's just going to cost them more. That's it.
No, it won't cost them any more. It'll actually cost them less because they can stop the AM transmitter, because the AM transmitter might be a megawatt, whereas the FM transmitter might only be 250 kilowatt. And that's continuous transmitter electrical power. So the FM radio station transmission already costs them less money than their AM transmitter.
So you're saying the only person that it's negative to is the advertisers.
Or people in regions where there's a lot of mountains and you need AM to penetrate the mountains.
That's it. Yeah.
Yeah.
Now, the other thing that we'll have to change is highway traffic information. If you've ever been driving along the turnpike and you see those billboard signs that say tuned to AM 1420 for emergency information,
Yes.
got the blinking yellow lights,
Yes.
that's because they already had access to that band and the transmitting equipment for public distress. So they just reused it to transmit traffic information. They can transmit it on FM, but then they have to go talk to the FCC into giving them a radio frequency. And remember, the AM transmission is very long distance. So if you have a 50-mile straight shot of the turnpike, you can have one transmitter that'll cover that entire length. But remember, any major highway, you go down the highway, every 1/10 of a mile, there's one of those little cement pole, little flat panel antenna, and a camera on it, and an antenna. So they've already got high bandwidth data communications going along there. They could just transmit on FM, not a problem. So I don't shed a tear for them, because they've been milking the marketplace for so long and trying to convince people that they have no alternative. It's going to cost them a fortune. Your car radio already has an FM receiver in it. You know what doesn't have an FM receiver in it? That should? Your mobile phone.
Yeah.
Mobile phones.
How long were you?
Mobile phones used to come with an FM radio receiver in them, because the same digital signal processing that processes the mobile phone with a little software tweak could give you digital FM radio in stereo. How come that went away? Streaming services. Why would I want to be AT&T and give you a free app that you could listen to FM radio at no cost, when I've got my own streaming service that I can charge you $9 a month to pick up on your mobile phone, but you get video as well as audio? So I stopped giving you the FM radio app for your AT&T mobile phone, or your Verizon, or your T-Mobile. They're all in the same ballpark. Because I have a mobile phone that at one time actually had an FM radio tuner app, and it was provided to me by AT&T. And then in a mobile update, the app went away.
I remember that.
Yeah. But I can listen to my iHeart streaming service, and I can pick up my local radio on that. And the reason why that's free, commercials. The FM radio station has commercials, and they can charge the advertisers more, because we're not only transmitting on radio your ad, we're transmitting on our streaming service your ad, so they can probably charge them an uplift fee for adding the commercial to the streaming app.
And by the way, they can track that you're listening to them, and you can
Oh,
get
yeah.
the information.
Who needs Nielsen Ratings Bureau? If I've got an app that I put on your mobile device and I want to know who's listening to my iHeartRadio FM station, I not only know you're using the app and when you're using it, because I'm the cloud service provider, I'm iHeart, but I can also tell and what radio station you're listening to. And then I can correlate that against advertiser revenue. Who wants to pay up more money to listen to that, talk radio program on iHeartRadio during the 6 to 7 p.m. hour when the money's better? Just business, folks.
But I like to listen to the AM radio because of, I don't know, because this is mono or the sound. I don't know. It's very soothing, especially when you listen to the traffic on the road, or if you listen to like emergency station, like the repetitive voice and the very, I like it. It's almost hypnotic. That is like a
emergency radios move from AM to allocated FM, and they've even gotten off of FM. They're on VHF and UHF, and now they've completely gotten off of that. And one of the big contracts that the U.S. government has with AT&T is the AT&T Now Network. The AT&T Now Network is a mobile phone service that has priority for first responders. So if there's some big event that happens, some emergency event, they can deny you, the consumer, mobile phone access to the benefit of first responders.
Yeah, I sometimes I listen to the Scotland or the British weather stations near to the ocean. It's just like they transmit in AM, but that is like a radio internet that you can listen to. It's very soothing. It's like you feel like you want to go to sleep. I like the sound of the AM radio.
Well,
I cannot even explain why.
It's the static. To give you an idea of
Maybe it's nostalgia.
to give you an idea of the FCC's take on it. For those of you that are familiar with WWV, that's that worldwide time signal.
Oh, yeah.
10, 15, 20, 25 hertz, megahertz. Well, there's so much electronic hash in the world, it's not worth it to look at 5 megahertz anymore. 10 megahertz is kind of the bottom of the barrel for WWV. Most people listen to it at 15 megahertz. Just keep moving up the dial, because the radio hash from all the electronics in the world, not just the electric vehicles, everything's spewing hash. You got to go to higher frequencies to get a clear signal.
Do you want to turn off the recorder?
Okay, give me a second. I will stop sharing. And I will now turn off the recording.